To discuss rotational equilibrium and Newton's first law for rotation, we should first take care to distinguish what we mean by translational or linear motion from what we mean by rotation. So if we're moving in 3D and we've got a system or a body that has a center of mass, a single point, in 3 dimensions, that point, the center of mass, can move left or right, up or down, backwards or forwards. So that kind of motion of the center of mass through space, that's known as translational or linear motion. And we are familiar with Newton's first law for translational motion. If the net external force on the system is zero, then the acceleration of that imaginary point, the center of mass, will be zero, meaning the velocity of the center of mass will be constant, and we distinguish two kinds of translational equilibrium. Either the VCM is zero, and we call that static translational equilibrium, if the CM is not moving at all, or if the VCM is a non-zero constant, so if this point is moving through space with a constant velocity, then we call that state dynamic translational equilibrium. All right, so mainly I'm introducing this term translational to distinguish the physics we're familiar with the related concepts for rotational motion, which we'll discuss now. So let's consider a rotating rigid body, like this disk that could be spinning here. And I want to reintroduce the concept of angular velocity, omega, as a vector. So if this disk is spinning about this axis, then its angular velocity can be represented as a vector that points along the axis of the rotation and points in the direction given by the right-hand rule. Let me explain what I mean by that. So here, seeing this disk spinning in this direction around the axis. If you imagine grabbing onto the axis with your right hand in such a way that your fingers curl in the direction of the rotation, then your thumb will point in the direction of the angular velocity vector. So if we're rotating this way around the axis, then the thumb points up like that, and your omega vector points in that direction. If, on the other hand, we reverse the direction of the rotation so that the disk is spinning the other way, then grab that axis with your fingers curling in the direction of the rotation, and your thumb will point in the direction of omega, down that way. So by reversing the direction of the rotation, we reverse the direction of that angular velocity vector. Okay, it's going to turn out to be useful to describe angular velocity as a vector in this way. As soon as we do that, we could then imagine introducing your angular acceleration as a vector as well. So the time derivative of this angular velocity vector is your angular acceleration vector. So alpha will be a vector for us now as well. Here are several possible relationships between your angular velocity vector omega and your angular acceleration vector alpha, if they happen to be pointing in the same direction. So we see this disk rotating in this direction. Grab that axis with your right hand, curl your fingertips in the direction of the rotation, thumb points in the direction of omega. So omega is pointing up in that direction along the axis. If alpha is also pointing in that direction, if it's parallel to omega, then that's going to indicate that the rotation rate, the magnitude of omega, will increase. This disk is about to speed up. On the other hand, if alpha is opposite omega, if they're anti-parallel to each other, that indicates that the magnitude of omega is about to decrease. So the rotation rate in RPMs is about to slow down. If, on the other hand, alpha makes some angle with omega that's not 0 or 180, so some intermediate angle here, then we will expect that omega, in this case, with this angle as acute, then a component of alpha is parallel to omega. That component will make the magnitude of omega increase. So this disk is about to spin faster. Oh, look at that. Okay, arrows pointing the wrong directions here. Okay, so this omega is pointing along the axis that way. So grab the axis, thumb with omega. Disc should be rotating in the direction of my fingers. So this arrow like that, but then this arrow is the wrong way. Okay, so the rotation rate of this is about to increase because of alpha, but this alpha also has a component perpendicular to omega, which is going to, over time, here's the situation a moment later, that component of alpha perpendicular to omega is going to cause omega to change direction. It's going to tilt. So this spinning disk is about to speed up, but also tilt because alpha makes this acute angle with omega. All right, in general, this is a fairly complex motion that would be treated in an intermediate level college physics course. So this sort of thing with alpha making a non-zero and non-180 degree angle with omega, this is generally not going to be treated in our introductory level physics course. So this is a bit beyond what we'll be focusing on. We'll be dealing primarily with scenarios like this, where alpha is either causing omega to increase or decrease, but omega is going to be fixed in direction. We generally won't worry about tilting axes of rotation for the time being. All right, so we've introduced omega and alpha as vectors now and discussed how they relate to the axis of rotation and the right-hand rule to relate a rotation direction to a vector direction. Now, let's discuss Newton's first law for rotational motion, the analog of this set of ideas. Newton's first law for rotation. Playing the role of force will now be torque. So if the net external torque on a rigid body is 0, then the angular acceleration of the rigid body is 0. So here we have the angular acceleration vector playing the role of the ACM vector. So in that case, the angular velocity of the rigid body will be constant. Omega will be constant. So omega here playing the role of the VCM. And then there are two possibilities we identify. Either omega is 0, which we call static rotational equilibrium, so the body is not rotating at all, or omega is some non-zero constant. We call that state dynamic rotational equilibrium, so rotating at a constant rate. These pictures illustrate those possibilities. The first one here, you got some disk that is simply not spinning at all, and there are no torques acting on it, so it'll be in static rotational equilibrium. It will remain not spinning. Here, we've got a disk that is spinning because sometime in the past some torques were exerted on it that got it rotating. So it is spinning about this axis, omega. Grab that axis with your thumb. Thumb points in the direction of omega. Fingertips curl in the direction of the rotation. This disk will continue to spin forever with that constant omega, as long as there are no torques acting on it. So this disk is in dynamic rotational equilibrium. A spinning object will remain spinning forever at the same rate until some net torque acts on it. This disk here, we've got rotating in this direction, as we can see by the omega vector here. Grab onto that axis, thumb with omega, fingertips are curling with this disk. This disk, however, is being driven by this belt. This belt turning this way is applying a torque to the disk. Here is that applied torque right there. That torque points along the axis. Put your thumb in the direction of the torque, grab the axis. That torque is tending to increase the angular velocity that causes a rotation in that direction of my curling fingers. So this torque is trying to increase omega. The turning belt here is trying to speed that disk up. But here I've indicated that there is also a frictional torque on the axis that this disk is spinning about. And that frictional torque pointing that way, put your thumb with that frictional torque, that frictional torque is tending to cause a rotation opposite the current actual rotation of the disk. So this frictional torque is trying to decrease the rotation rate. So those are in competition with each other. And if it is the case that the net external torque, being the sum of the applied torque from the belt, the drive belt here, and the frictional torque opposing it, if the sum of those is zero, if they're exactly equal and opposites, they cancel out, then net torque is zero, angular acceleration is zero, omega will be constant, and this disk will continue to rotate at a constant rate forever as long as the torques are perfectly balanced. So that disk is also in dynamic rotational equilibrium. All right, so big picture, you're familiar with Newton's law. An object in motion tends to stay in motion unless acted upon. Well, here we have Newton's first law for rotation. A rotating object will continue to rotate forever at the same rate unless acted upon by a net external force.